Welcome back. Here's part 3 of this PowerPoint presentation on 5 principles of genius thinking. So we've done principles 1 and 2, and we're in the middle of talking about principle number 3, engaging intellectual play. So this is probably a bit annoying, but I'm going to whip through the entire presentation up to where we were before. Up there we go. So here's my brilliant high school kids who've done clever things with the Galilean ratios, just playing with nomens and other variations of nomens. All right, let's carry on with more play. Here's a wonderful question. Is today opposite day? What must the answer be? Actually, think about it. There's only one possible answer to this question. All right. But this type of self-reference is very playful and often appears in mathematics. It comes in all sorts of places. Just some examples like, what's negative x if x is negative 50? That's a very tough question for students. It feels very self-referential. What's 7 to the log base 7 of 3? That is, here goes. What is 7 raised to the power that makes the answer 3? Well, I guess the answer is 3. What's sine of the inverse sine of 30 degrees? A lot of backwards thinking. And if you ever studied Cantorian set theory, consider all the set of elements that are not in their own assigned sets. That's very sort of self-referential and fabulous. But this idea comes up in math a lot. And it's hard. It's hard for kids, but it's also very playful. I think mathematicians will take great delight in self-referential things. Here goes. Here's a classic question. Why is negative times negative positive? And this is actually a very hard question to answer, especially in the grade school level. And I really don't have yet seen a satisfactory answer given to me in all my work that I've done with teachers. And it's actually hard. I don't blame it. It's actually tough. So probably one way around it is to actually be playful. So earlier on, we had multiplication was really represented as areas of rectangles. So let's have a wild idea. Let's allow rectangles to have negative side lengths. Crazy. Just being very playful here. So let's consider 17 times 18. So what we did before, we thought of that as like, instead of 17, we went 10 and 7, and instead of 18, we go 10 and 8. Much easier numbers, and I can see I've got 100, and 10 times 8 is 80, 7 times 10 is 70, and 7 times 56. I see I've got 4 pieces that add up to 306. So that tells me 17 times 18 is 306. Now comes the wild part. Let's do the same calculation again, but let's allow negative side lengths. So let's keep 17 as 10 and 7, but let's think of 18 as 20 and negative 2. Now, again, I still have 10 times 20. Now I have a piece 10 times 20, which is 200. I've got a piece that's 10 and negative 2 wide. Doesn't make much sense geometrically, but we're just having fun. In some sense, I can make sense that 10 groups of negative 2 would be negative 2 and negative 2 and negative 2 and negative 2, negative 20. Okay, that's fine. 7 times 20 is 140. 7 groups of negative 2, I guess, is negative 14. I feel kind of comfortable with that. And if you look at that, 200 and 140 makes 340, take away 20 is 320, take away 14 is 306. It's all consistent. The answer is 306 again. Or if you like, we can think of 18 as 10 and 8, leave it as it was before, but now think of 17 as 20 and negative 3. And look at the areas of each of the pieces. Negative 3 groups of 10, that's a little bit weird, but if I switch that around, think of it as 10 times negative 3. 10 negative 3s is indeed negative 30. I can handle that. And off we go. And lo and behold, those pieces as well still tell me the answer is 306. So if I do start being wild and allow for negative side lengths, I see the answer 306 is consistent. So let's now be wildly wild. Let's think of 18 as 20 and negative 2, and 17 as 20 and negative 3. And here comes, in full transparency, the culprit piece. What is negative times negative going to be? We need to work out negative 3 times negative 2 as we do this. That's the one that scares me. But I know the overall answer has to be 306. So let's do all the other pieces are fine. 20 times 20 is 400. 20 times negative 2 is negative 40. 20 times negative 3 is negative 60. And the mysterious piece that scares me, negative times negative. Well, look at it. 17 times 18 has to be 306. So far we've got 400, take away 40, take away 60. I've got no choice but to say that the math is telling me that negative times negative better be positive. The answer better be plus 6 in order for this to be consistent. So in some sense, there's actually an argument that the math is telling me that it wants negative 3 times negative 2 to be positive 6. And you can do this with many examples. And actually, that tends to be very satisfying for kids. The true reason why negative and negative positive actually goes into a little bit of abstract algebra. You need to understand what are the rules of arithmetic you like to believe in. And it turns out one of the consequences of those rules is this. It's all hidden behind the machinery of this diagram. But there's a way of being playful that can see that negative times negative really kind of wants to be positive. All right, so playing can really cement ideas. Let's go to something that's a high school level. So what are sine and cosine really? Well, it all came back from the days of ancient India when they were trying to figure out the paths of stars. They thought stars would go in great big circular arcs overhead, and then during the day they go in circular arcs underneath us and reappear in the east and go in circular arcs overhead. So they assumed that all motion was about circular motion. And a very basic question in the history of trigonometry is, how high are stars? And you can't get a rope and just measure the height of a star, but all you can do is just measure the angle you're looking at the star. So they invented this theory of circlometry. We're trying to work out the heights of stars in circles. So at each angle x, they try to work out the height of a star, and at some point they want to work out the companion length to the height, the overness of a star. They call that the sine and the cosine. And just to make the mathematics simple to get going, to get the theory going, let's assume we're on a radius of 1 unit. And therefore, there we have it. Sine and cosine are just the heights and the overness of a star as it goes around at different angles overhead. Great. And then, standard thing in a high school class is to have kids actually plot the sine graph. When the angle of elevation is 0, the star is right on the horizon, it has 0 height. When the star goes up to 90 degrees above me, it's at maximum height of 1 unit. And so we get this curve. So we have kids plot this curve. Great. Now, I like to be playful. What if stars were kind of funky? What if they followed square motion? So let's invent a notion of squine and cosquine. How would the graph of squine and cosquine appear? So again, this star is going to follow this square motion overhead and underneath me. I can look it up at a different angles of elevation x, and I'm going to ask what the squine and cosquine graph looks like. So let's just do squine here. It's kind of interesting. You see that at 45 degrees, the star is going to be height 1. And in fact, it's going to stay height 1 for a long while. In fact, you see that if you play with it for a while, there's going to be all these bands where the height of the star is 1 for a long while, or -1 if it's underneath me. So I can see the squine graph has these flat sections of 1. Now, ideally we should play with this for a while, but I can see obviously at angle 0, it has a height of 0, and somehow I've got to get up to these 1s. And if you're very careful, you see it does actually turn out to be these curved shapes like this, but that's not obvious. It isn't play. But having kids play with that really cements the idea that sine is just the height of a star. And in fact, you can have fun, put stars on other weird shaped motions, on diamond shaped motions, or triangular or pentagonal motions. It's fun to plot what the squine graph looks like there. Actually, if you really want a real challenge, while I'm being very boring during this talk, can you graph me for tank x, which I'll define to be squine over cosquine? What does the graph of tank look like? If you can figure that out, you're actually in for a bit of a surprise. It's kind of fun. Anyhow, that's being playful. All right, principle number 4, understanding trumps memorizing. That is just, if you understand something, you really need to memorize very little in life. And that's good for me because I really can't memorize stuff. In fact, I'm quite resistant to memorizing stuff. So it's actually sad that so much of our curriculum wants to train students to want formulas, to actually want them, and to be willing and plug and chug a lot. I think plugging and chugging is actually kind of dreary and joyless. But we've trained our kids to want to do that because it's actually safe. I understand that. So plugging and chugging is safe, but it actually is just dreary in my opinion. For example, working at the equation of a line. I think there are all these different names for different forms of equations of lines. What's like the slope-intercept form and the point-point form or the point-slope. I cannot get my brain to wrap around that. And I've been teaching algebra, so I'm a bad algebra teacher, I guess. But think about this. What is an equation of a line? Well, an equation is any old formula that must be true for a point xy to be on the line. So here's a line. I want to go through the point 2, 3. I want to have a slope of 7, and I want some formula that must be true for any old point xy to be on that line. So here's a point xy. I want it to be on the line. What must be true for that point xy to be on that line? Well, we like to believe that straight lines have the property that their slopes are always the same, no matter how you measure them. That rise over run is always the same, no matter where you do it. All right, if that's the case, then I can work. Whoops, we like to believe lines have rise over run. Let me work out the rise over the run in like the obvious spot in this picture. The 2 points I've got, the actual point 2, 3, and like the general point xy. So I want the difference of the y values and the difference of the x's is the y values, the rise over run to be the slope of 7 no matter what. Well, that gives me a formula. The difference of the y values, y minus 3, over the difference of the x values, x minus 2, must be 7. Voila! There's an equation that must be true for the point xy to be on that line. Done. Now, algebra teachers probably don't like having x minus 2 on the bottom because actually you might be in a bad position of dividing by 0 if x happened to be 2. So you might want to do algebra on that. Feel free. But there it is. That's the essence of it. We've done our task. Find an equation that must be true for any point xy to be on that line. If kids can handle that, I'd be so happy. The distance formula. Oh, this one drives me nuts. What is the distance formula? It's just Pythagoras' theorem. I want the distance between 2 points. Well, it'll just be whatever the horizontal leg is and the vertical leg is. That's just Pythagoras gives me the distances, the square root of those differences of x value squared plus difference of y value squared. So if I'm going to write, if a kid's asked me to remind them what the distance formula is, I just say Pythagoras theorem. If I really would need to be pushed further, I might actually redraw this picture and just say, okay, there's the formula. A lot of books, a lot of classes have kids memorize this version of the distance formula, and it's actually ugly in my opinion, and it's very confusing. Kids get the pluses and minuses completely mixed up. But if you understand it's just Pythagoras' theorem and have kids, teach kids the patience to just quickly draw a sketch on the side of the page, which I admit, this is the teenage world that I'm willing to do that sort of thing. But if that's a good life lesson, just pause for a moment before you leap into action. Things become clear, nut your way through stuff. But I agree, that distance formula is hard. All right, solve x squared plus 4x plus 1 is 86. Well, okay, we have them do the quadratic formula all the time. I don't have it in my head. I'm going to say this is really a geometry problem. It's about squares. In fact, there's an actual square in this formula, x squared. So there it is. There's my actual physical picture of x squared. I do admit this is actually more complicated. I've got more stuff going on. So I need to incorporate the 4x and the 1 somehow. But I want to keep it a square. Squares actually seems good to me. So let's incorporate the 4x. And to make it symmetrical, which feels good to me, I have to split this into 2x and 2x. So there's my square extended, and I need a 2x piece and a 2x piece. That means the side lengths I need to deal with are 2 and 2, as shown, which means the fourth remaining piece of the square better be a side length, an area of 4, which is a little problematic because my equation is x squared plus 4x, x squared got, 4x got, it's 2x and 2x, and I've got a 1, which is not a 4, which is very irritating. But here's a great life lesson. If there's something in life you don't like, just change it. I don't like that 1, I want it to be a 4, so let's make it a 4. Let's add 3 to both sides. Voila. X squared plus 4x plus 4 must be 89. I like x squared plus 4x plus 4 because what is it? It's all that work shows me it's really just a square. It's really x plus 2 squared, and off I go. X plus 2 is root 89 or negative root 89, so x is negative 2 plus root 89 or negative 2 minus root 89. Piece of cake. Much better than the quadratic formula, in my mind. Okay, let's find the inverse sine value of a half. That means do sine backwards. Instead of starting with an angle and finding the height of the star, this is backwards. So I've given you the height of the star, find the angle. So what this is really asking, if I understand what this question is, where does the star have a height of 1/2? Okay, well, in circlometry, I can see in my mind there's 2 places where the star is going to have a height of 1/2. And all I need to do is work at this angle. Okay, I understand that, piece of cake. In fact, I'm actually really kind of fun because I see a picture there that 1 and that half suggests I flip that triangle and make a little equilateral triangle, 1, 1, and 1 there in shaded blue, which tells me that angle better be half of 60 degrees, 30 degrees. Bingo, I have it. So I see that I'm basically dealing with a problem with 30 degrees. So there's 2 places where the star can have a height of 1/2, basically 30 degrees, and that's sort of on the other side, 180 minus 30 degrees, which is 150 degrees. Bingo. In fact, I can work through all these problems. And as you do this, yes, numbers do stick in your mind. Kids have been trained to memorize a half, root 3 over 2, 1 over root 2. Yes, they stick in my mind as well. That's fine. I have no objection to stuff sticking in your brain. But once they're stuck in your brain, then doing inverse tangent of 1 over root 3, for example, becomes easy. Think of that as a half over root 3 over 2. And then you can go from there. But there's an example of understanding, lets you nut your way through stuff. Great. I'd like everyone now to please memorize the following division rule for the number 9. How it works is as follows. Read the number from left to right and write down the partial sum of its digits. For example, 213011 divided by 9. The first digit is 2, so let's just write 2. Then look at the first 2 digits, 2 and 1. 2 plus 1 is 3, so we'll write 3 next. Then there's the first 3 digits, 2, 1, and 3, add up to 6. 2, 1, 3, 0, add up to 6 again. 2, 1, 3, 0, 1, add up to 7. And then finally, 2, 1, 3, 0, 1, 1, add up to 8. And we'll write the answer is 2, 3, 6, 6, 7, remainder 8. So the final sum is the remainder. Okay, I'd like you to memorize that rule, please, and now do these next 50 problems. Aren't you just burning to know why that works? I wish everyone was just burning to know why things work. All right, I'm going to leave that as a teaser because we're going to go to part 4 of this PowerPoint presentation. So hang on for part 4.